Hello everybody, this is Mr. Lowry, and we're looking at the notes and in-class assignment, or I guess I should say in-class examples, for 11-17. So if you missed today, then this is for you. If you need a little maybe extra help from today, or we didn't get to something in class, this is for you too. Okay, there are three main ideas that we're going to try to understand and then apply in our assignments here. These are all found in section 6-4 of your textbook. That's this guy. And this starts on page 307. The first idea here is the triangle proportionality theorem, which is kind of similar to an idea we talked about yesterday. So let's kind of talk through that. And there's actually a proof of this that we did in class, which I'll go over I think in a separate video. But this is the triangle proportionality theorem here, and this is on page 307. So if a line is parallel to one side of a triangle and intersects the other two sides in two distinct points, then it separates these sides into segments of proportional length. Well, that's a mouthful, but this is the idea. We start with a triangle, right? And we want a line that's parallel to one of the sides. So notice that if I had triangle, let's say ACE, right, and I drew another line inside of it, a parallel line, I get BD. Okay? Now the reason why that sentence is so long is it says the line is parallel to one side of a triangle and intersects the other two sides in two distinct points. So I don't want like a parallel line that's outside of the triangle. So imagine I had triangle ACE and I drew a parallel line to AE outside of here. That's not what we want. So that second piece of information, the fact that it intersects the other two sides in two distinct points, means that it has to be kind of inside the triangle. Okay, now when that's the case, what happens is this section, the ratio of this section to this section is equal to this section to this section. In other words, this parallel line cuts the sides of these triangles into proportional pieces. Okay? It kind of seems like we talked about that yesterday, and we talked about something similar, but yesterday we were talking about the sides of similar triangles. So we have two similar triangles here, CBD and CAE are similar triangles. We got this little guy here and then this bigger guy here. And those are similar, but we're not talking about the full side of the triangle. We're talking about the pieces of the sides of the triangle, which is a little bit different. Okay, so hang on just a second. I'm going to grab a piece of paper and I'm going to show you something. Okay, sorry about that. So I wanted to just draw this out because you can see the picture in the book, but if I can draw it like a piece at a time, I think it might make a little bit more sense. So let's say you have a triangle here. Okay. What we're doing is we're just basically cutting that triangle into pieces. So imagine I came by with a line. Now this line is going to be parallel to the bottom line, but imagine I came in here and I just kind of chopped off the top of that triangle. Okay. Well, what we're saying is that there's a proportion here. This to this is equal to this to this. Those pieces are cut into like proportional sections. That's what the theorem is saying. Now, we actually proved that in class. So the first thing we did here was we wrote down that theorem, so triangle proportionality theorem. Okay, and we drew a picture and we stated our given and our proof statement, and then we proved that idea. And then there's actually a proof there of that theorem in your book as well. It's a paragraph proof. It's very similar to the one I did. I just did a 2-column proof, but it uses a lot of the same ideas and reasoning. So part of your notes today should include that proof. What I'm going to do is I'm going to make a separate video explaining that proof and also giving you hints for how to prove the converse of that theorem, which was one of your homework assignments. Okay, so if you want to, you can pause the video there and write down this proof now, or you can come back in the next video or another video that I've posted. We'll talk about that proof and then a similar proof that you're going to do in your homework. Okay, the way we did the notes today is we stopped after that theorem, after we proved that theorem, and then we decided to practice with that theorem. So this bullet point says use triangle proportionality theorem to set up and solve proportions, and then I just said see example 1 and 2. So there's a handout today that goes with the notes. The reason why I give that handout is because it's kind of hard to draw triangles in a way where they look proportional, and we got proportional sides here. So this is the examples from in class, and I will post this for you. This is my worked out version, but I also want to kind of show you what I'm doing as I go. So if you're interested in this and seeing these example problems just like worked out, my work, you can kind of check that out. I'll post it, but let's take a look at a few of these. Okay, this is the way we did it in class. So after we talked about the triangle proportionality theorem, we did these two problems, and these use that theorem. So in the copy, I'm sorry, these came out a little bit light. These little lines here are marked parallel with these arrows, but it's hard to see that. So we know that we have a triangle, and we know that we have a line parallel to one of the sides of the triangle. And it's parallel, and it intercepts the other two sides of the triangle in two distinct points. And that's what the theorem says, right? If a line is parallel to a side of a triangle and intercepts the other sides of the triangle at two distinct points, then that line cuts the sides of the triangle into segments of proportional length. Okay, so that's what the theorem says. It's kind of wordy. What that means, though, is the ratio of this section to this section is equal to the ratio of this section to this section. That's what proportional means, right? It means equal ratios. So again, this line here kind of cuts this triangle, and it cuts the sides into proportional segments. Okay, so from here, you can do a couple different things. I would recommend simplifying that ratio first and then cross-multiplying. So the way I did it was to write 14 over 7 as 2 over 1 and then cross-multiply. That gives you 22, so 22 times 1, and then 2 times negative x plus 24. Whoops. I want to make sure that I'm multiplying that whole binomial by 2. Okay, so I'm going to come up here, sorry. I have 22 equals negative 2x plus 48. Okay, and I'm just going to solve that for x. So let's subtract 48 from both sides. That's going to give me negative 26 equals negative 2x. I'll divide both sides by 2, and I'll get 13 equals x. Sorry, that's a 13. Looks like a 3. The box there kind of ran into my 1. All right, so that's how it's done. Now, number 2 is very similar idea. The difference here is that you have to figure out what this section is before you do anything else. So if this whole side of the triangle is this measurement, and this piece is 9, I can do this minus 9 to give me this piece. So negative x plus 32, that whole length, minus 9. Now, I can keep these in parentheses because it's a binomial minus 9, but I'm not going to have to do any distribution or anything here, so I really don't need them. I get negative x plus 23 for just this section. Okay, so now I can set up my proportion, right? I got parallel lines. This line is parallel to one of the sides of the triangle, and so it's going to cut the sides of the other two sides of the triangle into proportional parts. So there's several ways I can set this up. I can go 6 over 8 equals 9 over this, or I could go this over 9 equals 8 over 6, or whatever. Just make sure you do kind of, if you're going, when you're picking the sides, do them in the same order. But let's do 8 over 6 equals negative x plus 23 over 9. I believe that's how I set it up in, I set it up a little bit differently in the document that I'm going to post, but that's okay. It's good to see that there's multiple ways of doing it. You're actually going to end up with the same thing. So maybe reduce this ratio here, so that's 4 over 3. Okay, now we can cross multiply. So that's going to give us negative 3x plus 69 equals 36. So 3 times this guy, right, distribute. 3 times negative x is negative 3x. 3 times 23 is 69. 4 times 9 is 36. Okay, now let's subtract 69 from both sides. And we'll divide both sides by 3. Sorry, divide both sides by negative 3, excuse me. And we'll get x is equal to 11. Okay, so that is an application of the triangle proportionality theorem. So those are your example problems for that theorem. Okay, now the next place we're going to go, you can see this in the notes here. Also, all these notes are posted in Canvas for you. We're going to go to corollary 6.1. So remember that a corollary is basically a little bonus theorem. Sometimes you prove a theorem and then all of a sudden you get like kind of an extra piece or like a special case or something like that that also works. So it's like a bonus result that you get from proving a theorem. So this is corollary 6.1, and this you can find on page 309. The way I drew mine is slightly different, but I'll show you where that's at in the book and we'll kind of explain there as well. Okay, so here's the corollary in the book, 6.1. It's on page 309. So if 3 or more parallel lines intersect 2 transversals, then they cut off the transversals proportionately. Okay, what I wanted to point out to you is that this says corollary 6.1 is a special case of theorem 6.4. Okay, so the 6.4 is the one we just proved, the triangle proportionality theorem. This is just a special case of that. If you kind of ignore some of the extra lines, you'll start to see triangles within triangles. So if I kind of ignore those extra pieces of that transversal, and I ignore this stuff, and I ignore this stuff, you get like 3 triangles all kind of embedded in each other. So I'm going to show you that over here. So in the notes, I drew the picture just a little bit differently so it looks more like the picture that we drew before. So imagine this for a second. Imagine that these lines keep on going, right? And they're going to eventually cross, and we're going to form a triangle. And if we get rid of some of this stuff, you can see that it's like a Christmas tree kind of thing, right? We have like basically a triangle, and it's getting cut into pieces. And it doesn't actually matter where those cuts are, they don't have to be equally spaced. But when we cut the triangle into pieces, those parallel lines are going to make proportional sections. So like the ratio of this piece to this piece is going to equal the ratio of this piece to this piece, which is going to equal the ratio of this piece to this piece. It's basically the same thing we just talked about. So in this case, we can say that like AB to DE, AB over DE is equal to BC over EF. There's actually several different proportions we can talk about, because we can also we can say that like AC over DF is congruent to AB over DE, because there's like all these different triangles. There's like the top triangle, and then there's this triangle, like the medium triangle, and then there's like the big triangle, right? And so we can kind of separate all those into like basically proportional sections, essentially. So that's kind of what we get from there. Again, this is very similar to what we just proved in 6.4, and so we're just going to apply this. And the examples that we're going to do, we're going to look at in your example problem handout here is 5 and 6. So if we go to this guy here, the note here is we're going to use corollary 6.1 for this. Okay, so I'm going to add some stuff here. Now these little symbols are actually already here. I'm sorry, with the copy that I made, it just made those really light for some reason. I think they were like pink or red in the original document, and so when I printed it printed them kind of light. But those are arrows that are marking these guys parallel. Okay, the other thing that I'm going to do is I'm going to extend these lines here to make a triangle, or like a set of triangles within other triangles. And that'll, I think, match a little bit better to what we've been talking about. Sorry, it's a little rough, but You get the idea. Okay, so really what we have is we just have like a top triangle and like a bigger triangle and then like a biggest triangle. And those parallel lines are going to cut the sides of the triangle into proportional sections. So I can set up a proportion using these values. I just don't know this one. I do know, though, that this distance is 14. So if I do 14 minus 8, I'm going to get 6. So the proportion I'm going to set up is something like, 6 to 8 is the same as 2x minus 5 to 12. So that's one way to set it up, not the only way. You can go 8 over 6 equals 12 over 2x minus 5 or something like that as well. Just make sure that when you set up your proportion, you are consistent in the order that you do. So if I'm going like top to bottom, I'm going to go top to bottom here. If I go bottom to top, I should go bottom to top on the other side. All right, so we got a ratio, or excuse me, a proportion here. So let's simplify the one that's easy to simplify. We'll make our life easier. And then we'll cross multiply. So 3 times 12 is going to give us 36. And then we're going to do 4 times this stuff. So remember, we're going to have to distribute here. So 4 times this binomial expression, we're going to do 4 times 2x. And we're going to do 4 times negative 5. Okay, we'll add 20 to both sides. And then we'll divide both sides by 8 to get 7 equals x. Okay. We'll do the same thing over here on this side. So again, I'm just kind of like extending lines to kind of create my triangle. That kind of helps me see what's happening here. And then these are marked parallel. Okay, so something like that. So again, these parallel lines that, like, let's say you have this original triangle, and you got these parallel lines that are cutting through this triangle. They're going to cut the sides of the triangle into proportional pieces. I just got to figure out what some of those pieces are in order to help me set up a proportion. Now, in terms of the theorem or the corollary that we're using, we can actually do this a couple different ways. The way that the theorem is written, we can actually, in the book, we can actually do this, the ratio of this to this is the same as this to this. So we could actually set up a proportion with the information that we have available right now. Because like I said, the proportion that you can set up, you can use all different kinds of pieces. Like you can do this to this, or this to this, or this to this. There's lots of different relationships in there. But the way we did it in class, just to kind of make sense to us, kind of make it similar to what we've been doing, is to just find this missing piece here. So 18 minus 12 is going to give me 6, or 6 and 12 together make this full 18. Now over here we have 24, and then we have this length is negative 8 plus 3x. So if I do 24 minus this, I get this guy. Okay, so 24 minus, now this is where we have to be a little bit careful. If we're going to subtract this expression, we got to do it like this. And then we have to kind of distribute the negative here. So this is going to be 24, and then a negative 8, or a plus 8, and then a negative 3x. So altogether, that is 32 minus 3x. Okay? All right, now that's not the only way to do this problem, but I think it's the way that a way of doing it consistently with the other problems that we've been doing. Okay? So let's set up a proportion. Lots of ways to do it again. Just make sure that we're consistent in our direction. So I'm going to go 6 over 12. Actually, you know what? Let's do 12 over 6 because that'll be easy. I'll make a 2. So 12 over 6 equals this guy over this guy. Okay? So let's simplify the fraction to 2 over 1. I guess I should call it a ratio, but, they're both rational numbers. They kind of work the same way. All right, cool. So now we're going to cross multiply. So I got 2 times this stuff at the bottom. I'm going to come up here. So 2 times 32 minus 3x equals 1 times this stuff. And so, 1 times anything is just itself. That's negative 8 plus 3x. So altogether, that's going to be 64 when I distribute, minus 6x equals negative 8 plus 3x. Okay, if we group all the x's on the right, I would add 6x to both sides. And so 6x plus 3x. Okay, and then I'm going to add 8 to both sides to get rid of that guy. And that's going to give me over here 72. Okay, divide both sides by 9, and we get 8 equals x. Okay, so then, again, that's corollary 6.1. It's basically theorem 6.4 with some extra lines, extra parallel lines in it. Okay, the last idea here that we talked about is theorem 6.6. And you can find that in your textbook on page 308. It's at the bottom of 308. Right here. Triangle midsegment theorem. So first of all, we kind of have to understand what a midsegment is, and then we can understand what this theorem says. So I'm going to jump back to my handwritten notes so I can draw on them and stuff. Okay, so first let's talk about a midsegment. And it defines this in your book. But if we have a triangle, we can make the midpoint of some of the sides. So right here what I've done is I got this triangle ABC. And I found the midpoint of AB. I put it right there, and I called it D. So if it's a midpoint, remember it's going to cut these two pieces into congruent sections. This is going to cut AB into two congruent segments. Okay, I did the same thing on the other side. I took segment BC, the whole side of that triangle, and I found the midpoint, and I called it E. And since E is a midpoint, again, it's going to cut BC into two congruent segments. So D and E are midpoints, and we already knew what that meant, but when I connect those midpoints, I get what's called a midsegment. Okay, so right here, this guy is just kind of explaining what a midsegment is. So D is the midpoint of AB, E is the midpoint of CB, so E is the midpoint of CB, and that means that DE is a midsegment of ABC. So that's kind of just like a definition, but this is what the theorem says. A midsegment of a triangle is parallel to one side of the triangle, and its length is 1/2 the length of that side. All right, let's see if we can unpack that. So here's the midsegment. Okay, so this midsegment is actually parallel to this side, parallel to the bottom, and it's half the length of this guy. So it's parallel to AC, and it's half of AC, or its measure is half of the measure of AC, I should say. Right, so the reason why is you actually, when you draw that parallel line here, you're going to get similar triangles. The top triangle and then this triangle that the top triangle is sitting in are going to be similar triangles. And if you have similar triangles, you have some congruent angles. The corresponding angles are congruent. Or excuse me, the corresponding angles are congruent. And if those corresponding angles are congruent, you can show that these lines are parallel, because with parallel lines, the corresponding angles are congruent. I know, it's kind of weird. So that's how you get them parallel. Now, if you think about the scale factor here, this triangle is half the size of this bigger triangle, right? So there's a scale factor of like 1 to 2. The little to the big is a scale factor of 1 to 2. So this little guy is half of this one, and this little guy is half of this one. And since we have similar triangles, it makes sense that this guy right here is half of this one. Okay, so that's what the theorem says. It kind of requires a proof, but we didn't have time to prove this in class today. So I just kind of like wrote out this idea. This is the wording in the book, but what I said here is kind of a summary. Since DE is a midsegment, we can include that DE is parallel to AC and that DE is half of AC. It's half the distance. Okay, so we're not going to prove that one right now, but we will use it to solve some problems. And so in our class today, we said, okay, let's go back to the notes, problem 3 and problem 4 in the in the handout that goes with our notes. Okay, so again, the copy came out really light, so that's kind of hard to see, but these are actually marked congruent. I didn't add that myself. That was part of the original problem. But what I can conclude from that, if I have, congruent segments here, is that this is a midpoint, and here I have a segment, and this is the midpoint as well. So like these congruent sections tell me that this is the halfway point of DE. So K is the midpoint of DC, J is the midpoint of DE, and that makes this a midsegment. Okay? So what do we know about midsegments? Well, the first thing that theorem tells us, theorem 6.6, or the triangle midsegment theorem, is that this midsegment has to be congruent to, not congruent, parallel to this side of the triangle. So those are parallel. The other thing we know is that this length is half of this length. Okay? So there's actually a couple ways to set this up. We can say that JK equals is half of EC. That's one way to do it. And then we can solve the equation from there. The other way we can set this up is we can just do it the other way around. If this is half of this guy, then this guy is 2 times this one. So you can also say 2x plus 19, or sorry, 2 times 2x plus 19 is x plus 14. So whether you want to take the little one and double it to get the big one, or half the big one to get the little one, either way it's going to be the same thing. So we're going to solve these equations either way. I think the way I did it in my my handwritten copy that I posted is to multiply both sides of these by 2. So what's going to happen here is that the 2 times the 1/2 is going to equal 1. So the reason I multiply both sides by 2 is to cancel out that 1/2. So then I distribute over here, and I get 4x plus 38 is equal to x plus 14. So 2 times 1/2 is 1, and that's why I did that, to cancel that out. Okay, if you do it that way, you can group the x's on the left now, minus x. That's going to give you 3x on the left. Subtract 38 from both sides. That's going to give you negative 24 on the right. Divide both sides by 3, and you get x equals negative 8. Okay, now we have to be careful to think about what we're looking for. In problems 1, 2, 5, and 6, we were looking for x. But in this problem, it's asking us to find the measurement of this segment, kj. So I'm going to take that negative 8 and plug it back into this expression to find the actual measure of that segment. So 2 times negative 8 plus 19 is negative 16 plus 19, which is 3. All right. Okay, one more on this one. So we got these congruence markings were part of the original problem. They're just too light. It's hard to see them. But that means that this and this are midpoints, which makes this guy a mid-segment. Okay, again, what we know about mid-segments from that theorem we just read is that they're parallel. The mid-segment is parallel to one of the sides of the triangle. And we also know that this length is half of this length, or that this length is double this length, however you want to go. So you can either short times 2 equals long, or long divided by 2 equals short. Kind of up to you. The way the wording of the theorem says, it says that the long one is half the long one is the short one. Okay, so this is my setup. The mid-segment is half of the length of the side of the triangle. So to get rid of that 1/2, I can multiply both sides by 2. These will cancel. I get 2x equals x plus 8. Then I'll subtract x from both sides. And I'll get 1x equals 8. Okay, remember I'm not looking for x, although I need it. I need to find SU. So x plus 8 equals SU, or 8 plus 8. When I substitute 8 back in there, I get 8 plus 8, which is 16. All right, so those are basically what you're going to be doing in your homework for the most part. There is one proof, but we're going to talk about that in another video. So here, what you have is these are marked parallel. I'm sorry, these are very light. Those are marked parallel. These are marked parallel. So in problems 2 through 6, you can assume all these lines are parallel. They're actually marked parallel. It's just in the copy it came out really light again, so sorry about that. But yeah, you're going to have, basically you're going to set up proportions with these sides. So like 10 over x is equal to 25 over 49 minus x, or whatever. Or you could do like x over 49 is equal to 10 over 35. So just using those theorems that we talked about, I'm going to set those up and solve your proportions. Okay, on the back, these are about mid-segments. Okay, so again, these came out really light. I'm sorry about that, but the sections are marked congruent. So in these problems, 7 through 10, you can assume that you got mid-segments here. All these guys are mid-segments. And so you got to go like long times a half equals short, or short times 2 equals long, and set up your equations and solve there. Okay, now we do have a theorem that I'm going to have you prove. It's actually the converse of theorem 6.4. So 6.5 is the converse of 6.4. And in another video, I'm going to prove 6.4 with you, or go through that proof with you, and then help you set up the proof for 6.5. Okay? Thanks for watching, guys. I will see you in class soon, hopefully.